And so we will study number 1, electric field set up due to the dipole. Okay, first of all, I would like you to draw the dipole. A plus charge and a minus charge. The dipole will go from the minus to the plus. And let's suppose I want to find the electric field due to this dipole at this point P. Okay, so I can draw the field due to this and the field due to this. And I will call this angle theta. And I will call this angle theta. And this will become my P. And may I write, before I do anything else, over here, will my cosine theta be, if this distance is d, d over 2 divided by r. Cosine theta is base over hypotenuse. If this distance is r, may I also write this as d over 2 square root of x squared plus d over 2 squared? May I also write E plus or minus, both, as KQ over R squared magnitude? Or KQ over x squared plus d over 2 squared. Principle of superposition says that E at point R will be the field due to plus and minus. Okay, now watch carefully. This is a minus. This arrow needs to be going in here, right? The field point inwards. This arrow will be that way. So note, I'm going to move this a little bit down so I can make it bigger. What will this angle be? And what will this angle be? Are they both thetas? So may I write this as E cosine theta plus E cosine theta? Head to tail rule? Or 2E cosine theta? Or 2 KQ over X squared plus D over 2 squared times, oh, where did my D go? There should be a D over 2. Oh, I missed it up there. Okay. Or D over 2 divided by X squared plus D over 2 squared square root from here and here. May I simplify it in one step? Whew, breathe. The 2's get canceled, and I am left with K, Q, D divided by X squared plus D over 2 squared 3/2. Drum roll. What is QD? P. So this you can replace with a P. So just make another box and put it in there. E at point R will be KP over X squared plus D over 2 squared 3/2. Now that is a scary looking equation. Let's simplify it. For most cases, you only deal with what is called the limiting case. And what is the limiting case? X is much, much bigger than D. When X is much, much bigger than D, can I use the binomial expansion? And then you ignore everything else? So what will this become? I should rewrite E as a function of R as KP divided by X cubed 1 plus D over 2X squared 3/2. Take X squared common from the denominator. Stare at it. So basically what I've done is it's X squared plus D over 2 squared to the power 3/2. I took X squared common. So it'll become 1 plus D over 2X squared 3/2, which gives me this. Do you guys see that? Okay, so I'm going to erase this. So what will I get? KP divided by X cubed 1 plus minus 3/2 D over 2X to the power squared. And what I did was KP over X cubed 1 plus D over 2X squared minus 3/2. And drum roll, I am left with KP divided by X cubed 1 minus 3D squared divided by 4X squared. When X is much, much, much larger than the separation, which is normally the case, the second term almost goes to 0. Like d over x squared, right? It's very, very, very tiny. So then that means E at R can be written as, so note, E for a dipole varies as 1 over r cubed. So E for a charge, like a point charge or charges, varied as 1 over r squared. E for a dipole varies as 1 over r cubed. Take a wild guess. If you had a quadrupole, what do you think that would vary as? So a quadrupole looks like this. 1 charge here, 1 charge here, 2 charges here. So suppose this is plus, plus, then minus 2 cubed. What do you think E for a quadrupole varies as? What do you think? So for 1, it was 1 over r squared. For 2, it is 1 over r cubed. For a quadrupole, what do you think it will be? What's the next number up?
4.
There we go. It's literally 1 over r4. And that's what a quadrupole looks like. And we will do this on Monday.